So, when I say chemical reaction, what's the first thing that pops into your head? Probably a scientist in a lab coat, right? Bubbling beakers, fancy equipment, the whole deal. But what if I told you that some of the most amazing chemical reactions are happening right now, in your kitchen, or even inside you? Today, we're going to uncover the hidden chemistry that's all around us. Here's the game plan for today. We'll start off in the kitchen. Then we'll learn how to spot a reaction in the wild. After that, we'll get into the language of chemistry, figure out its most important rule, and finally, check out a couple of basic recipes for reactions. Sound good? Let's jump in. All right, first up, chemistry in your kitchen. We're starting with stuff you see literally every single day, but maybe you just don't think of it as, chemistry. Think about it. You ever leave milk out in the heat and it goes sour? That's a chemical reaction. Or what about the reddish-brown rust on your iron tawa? That's another one. From cooking your food, to your body digesting it, to just breathing, it's all chemistry, yar. The main thing to get is that the original stuff is turning into something completely new. Okay, so if this chemistry stuff is happening everywhere, how do we actually spot it? Well, that brings us to our next section, the signs of a reaction. Think of these as clues, and we're all about to become chemical detectives. So what's the secret? How can you tell for sure that a chemical reaction has actually happened? What are the dead giveaways? Let's break down the 4 big clues you need to look for. Clue number 1 is a change in state. Now, I don't just mean ice melting into water. We're talking about when a reaction creates a brand new substance that's in a different form. Like when you light a candle, the solid wax turns into gases like carbon dioxide and water vapor. That's the kind of change we're looking for. Clue number 2, a change in color. This one is super obvious. Remember our iron tawa? It starts off dark gray or black, but that rust is a completely different reddish brown. That color change is screaming at you that a new substance has been formed. Our third clue is seeing a gas appear out of nowhere. If you've ever dropped an Eno tablet into a glass of water, you've seen this happen. All those bubbles, that fizzing, that's a gas being created right there, telling you a reaction is going on. And the final clue, a change in temperature. Some reactions get hot all by themselves, releasing heat. Others do the opposite. They get really cold because they absorb heat from their surroundings. So if things heat up or cool down without you doing anything, chances are you're looking at a chemical reaction. Okay, so now we know how to spot a reaction, but how do we talk about them? How do we describe them in a way that's simple and everyone around the world can understand? Well, that's where the language of chemistry comes in. Just look at this sentence on the screen. It's accurate, sure, but it's a bit of a mouthful, isn't it? Imagine being a scientist and having to write that out every single time. No way. They needed a better, faster way to say the same thing. They needed a shorthand. The first step to making things simpler is this, a word equation. On the left, you have your starting materials, the reactants. On the right, you have what you end up with, the product. And the arrow just means turns into. See? So much cleaner, right? But why stop there? We can make it even shorter and more powerful by using chemical symbols. This is a chemical equation. It's the gold standard. It's totally universal. A chemist in Mumbai and a chemist in Mexico can look at this and know exactly what's going on. It's packed with information. So now we have our shiny chemical equation. But there's one more absolutely critical step we need to take. This brings us to the balancing act and to one of the most fundamental, unbreakable rules of the entire universe. Let's look closer at that equation we just made. Let's do a quick head count of the atoms. On the left, we have 1 magnesium atom and 2 oxygen atoms. But on the right, we only have 1 magnesium and 1 oxygen. Wait a minute, where did that other oxygen atom go? Did it just vanish? Of course not. Atoms don't just disappear into thin air. And that's because of this law right here, the law of conservation of mass. It basically says that you can't create or destroy matter in a chemical reaction. The atoms just get shuffled around into new patterns. So the number of atoms you start with has to equal the number of atoms you end with. So, how do we fix our unbalanced equation? We balance it. And honestly, it's just like solving a puzzle. The only rule is you can't change the formulas. H2O is always H2O, but you can change how many of each molecule you have. You just add numbers in front until the count for every element is the same on both sides. And there it is, the balanced equation. Now, if you do the count, you'll see everything matches perfectly on both sides of that arrow. The cosmic accounting is done. It's all balanced. Perfect. Awesome. So now we can spot reactions, we can write them down, and we can balance them. Now for the really fun part. Let's look at a couple of common recipes or types of reactions that chemists use to organize everything. We'll start with two of the most basic ones. You have combination reactions, where two or more things come together to make one single, more complex thing. And then you have the complete opposite, decomposition reactions. That's where one big thing breaks down into smaller, simpler pieces. So one is about building up, the other is about breaking down. Simple as that. Here's a perfect example of decomposition. You take this one substance, ferrous sulfate, you heat it up, and bam, it breaks apart into three totally different, simpler products. One reactant becomes three products. And here's combination in action. You add water to this stuff called quicklime, and they combine to form one new product. And hey, notice that word heat at the end? That's our fourth clue, the change in temperature we talked about earlier. See? It all comes full circle. So there you have it. We've gone from a rusty tava all the way to a law that governs the entire cosmos. We've learned the language to spot, write, and balance the amazing stories of how matter changes. So the question is, what chemical stories will you notice happening around you today? Thanks for watching.